Hello everyone and welcome to our webinar about the benefits and basics of sample preparation by Fusion. My name is Chantal Audet. I am the product manager for the Fusion instruments at Chemist, and my co-host for today's webinar is my colleague Philippe Daigle, who is the product manager for Fusion applications and consumables. Good morning, Philippe.
Good morning, Chantal. Welcome everyone to this webinar.
So today's presentation is a special request from many of our customers and partners who wanted to become more familiar with the sample preparation by Fusion techniques. The first part of this presentation will be an introduction on the benefits of Fusion for both ICP and XRF analysis. This will be followed by the review of the key factors that should be taken into consideration to be successful in your sample preparation by Fusion. The total duration of the webinar will be 30 minutes.
You can use the chat box located at the left of your screen to submit your question at any time during the presentation. We will have about 5 minutes at the end of the presentation to answer the submitted question. If we don't have time to answer all of your questions at the end of the presentation, we will make sure to answer your questions individually in the upcoming days.
Let's start this webinar by talking about sample preparation for XRF analysis. Depending on the state of the sample, whether it is liquid or solid, as well as on the requested degree of precision and accuracy, there are many different ways to prepare these samples. In this presentation, we will focus on the preparation of solid samples such as mineral concentrate ashes, or on the preparation of manufacturing materials such as cement, catalysts, and many others. We will compare the two following preparation methods, press pellet and fusion. As illustrated in the figure, these samples need to be previously grinded for all those three preparation methods: loose powder, press pellet, and fusion. Now, what do you need to prepare your samples by Fusion? Here is the most commonly requested equipment. To start, you need borate flux, in which the sample will be dissolved. Depending on the application, you might need other chemicals called additives, such as oxidizers, non-weighting agents, fluidizer, or internal standards. You will also need platinum ware. A few different alloys can be used, but the most common is the 95% platinum, 5% gold, which is well known for its durability and stability. It is also not wet by the molten mixture during the fusion process. An automated fusion instrument should be used in order to ensure safety and higher productivity. This instrument can be heated by gas or electricity. At Chemist, we offer resistance heating fusion instruments such as l'Neo, which can prepare one sample at a time, the Egan 2, which can be used to prepare two samples at a time, and the Diox fusion instrument, which can prepare up to 6 samples at a time for higher productivity. We also offer the M4 fusion instrument, which is heated by gas, liquid petroleum, or natural gas. It can prepare 3 samples at a time.
There are also many ways to prepare your sample for ICP analysis. Let's divide them in 2 categories. The first category is acid digestion, that includes hot plate acid digestion, block digestion, bomb acid, and finally microwave. These techniques use strong acid like nitric acid, aqua regia, and even hydrofluoric acid. The second category is sample preparation by fusion, either lithium borate fusion or peroxide fusion. These techniques allow you to dissolve metals and other non-oxide samples quickly and rapidly. You can then get rocks, catalysts, ceramics, lime products, and many more in solution without HF or other strong acids.
The only change regarding equipment when comparing borate solution with sample preparation for XRF is that you change the platinum mold for a Teflon beaker. For peroxide fusion, you need sodium peroxide, which is the most common solvent used for this application, but sodium carbonate can also be used for some applications. The crucibles that are the most frequently used are made of zirconium or nickel. As for the two previous methods, it is possible to use gas or electric fusion instruments. The neofusion instrument and the aux can be used to prepare peroxide fusion. Also, we offer the peroxide fluxer instrument, which is powered by gas and fully dedicated to peroxide fusion.
Sample preparation by fusion is a very simple technique. If you want to do a borate fusion, you must weigh your sample in the 95% platinum, 5% gold crucible, in which you also add the borate flux. The borate flux can be lithium borate, lithium metaborate, or a mixture of both. Also, you might need to add an additive such as a non-wetting agent or an oxidizer. You heat up this mixture to melt the borate flux and have the sample dissolved into it. Note that only oxide samples can be dissolved into the borate flux. However, any sample can be oxidized using an oxidizer or an oxidizing technique. Now, once your sample is dissolved into the molten borate flux, you have two options. You either pour the mixture into the platinum gold casting mold or into a diluted acid solution. For peroxide fusion, once the sample has reacted with the peroxide in the zirconium or nickel crucible, the mixture is dissolved using ultrapure water. Diluted acid is then added volumetrically to get the same acid concentration as used on the ICP.
Now, let's talk about the benefits of using sample preparation by fusion for XRF analysis. Just before we start, we wanted to show you a statement taken from a text written by Mr. John Anselmo and collaborators that was published in the Spectroscopy magazine. This sentence summarizes and clearly identifies what are the requirements for high accuracy results. In fact, as mentioned in this article, XRF is a comparative technique, and the closer the standards used to prepare the calibration curve are to the mineralogy, particles homogeneity, particle size, and matrix characteristics of the unknown, the more accurate the analysis will be. Having said that, we have to keep in mind that the standards used when preparing an XRF calibration curve should be similar to the unknown samples that need to be analyzed. When preparing natural samples such as minerals, clay, or geological and soil samples, it is practically impossible to know if the standards and unknown will be metric match. It is also the case with industrial products that can be mixed together with natural samples such as blended cement, polymers with different additives, catalyst, electronic, and composite materials. Fusion is the solution to this issue, and we will prove it in the next slides.
Now take a look at this graphic that illustrates the mineralogical effect. We can see here how the XRF intensities are affected by the different mineralogy of iron in press pellet. Also, in natural materials, the composition of mineral deposit varies from one location to another. There are also substitutions of various elements such as contaminants in the crystal structures. Consequently, it is almost impossible to closely match the matrix of standard to unknown using the press pellet technique. Therefore, highly accurate analysis at high concentration levels are difficult or simply impossible to obtain for many natural materials. Now, if we look closely at the press pellet surface, that's what we see, roughness and inhomogeneity of the specimen. The grinding of different mineralogical phases and composition produces particles that have different size and shapes and which will react differently when the pressure is applied to produce the pellet. This most probably leads to segregation of different materials of the sample with different density distribution. This will affect the penetration depth of the X-ray for a given wavelength of interest. This illustration shows that the effective layer is not homogeneous and not representative of the overall sample composition.
Sample preparation by fusion is the perfect method to eliminate these mineralogical and particle size effects. The pressed pellet contains different crystal structures. However, as illustrated here, glass discs are ideal for XRF analysis since they are vitreous and the components to be analyzed are homogeneously distributed in the glassy matrix. Using fusion makes the calibration easier. As you can see on the first graph, the particles size and mineralogic effects lead to calibration spread and to poor accuracy if you compare it to a calibration curve made with fused glass disc. As a matter of fact, the calibration is no longer limited. It can be applied to a larger range of composition. The calibration can also be made with synthetic standards, and it allows the application of matrix correction where it was previously not applicable. You can see here calibrations made by pressed pellets and by fusion for three different production sample types, which are A, B, and C. We see that with pressed pellet, you will need three different calibration curves in order to fit without the mineralogical effect for the three different types of samples, which contains the same component, here silicon dioxide. With fusion, a single calibration curve is needed, thus reducing time to calibrate and lowering the costs. This table summarizes the benefits of sample preparation by fusion compared to pressed pellet. As we discussed, using fusion eliminates the particle size and mineralogical effect. It leads to the following benefits: less grinding prior to sample preparation, increased accuracy, possibility of using synthetic standards for calibration, a wider calibration range, and application of matrix correction. It is important to know that within a webinar time frame, we merely discussed the concept of XRF analysis. If you wish to have more information on these concepts, you can register to workshops offered by your XRF supplier or other organizations in your local area.
We will now cover the benefits of using sample preparation by fusion for ICP analysis. We will start with peroxide fusion. We will show you a quick video of how to perform such method. First of all, in a zirconium or nickel crucible, you weigh the sodium peroxide or carbonates that will be used to oxidize your sample. Then you add your sample in the crucible. Place the crucible on your sample preparation equipment, as you can see on the video that shows a peroxide fusion instrument. You heat up the mixture at a temperature of approximately 500 Celsius degree to let the sample react with the peroxide. You let the mixture cool down when the reaction is completed. Once everything is cool, you either soak the crucible into ultra-pure water or rinse it over a funnel with the water used to rinse the crucible with the sample, so everything gets directly transferred into a volumetric flask. Finally, you adjust the volume so you get the exact dilution you are looking for. With this short video, we can notice that even though there is a manual dissolution step, the fact that the fusion itself takes only 5 minutes still makes it a method with a very fast turnaround. You can count about 10 minutes from the start to the end where the sample is fully dissolved. The manual dissolution step can be processed as batches, thus saving even more time. This is very simple and doesn't require any strong acids such as perchloric acid or hydrofluoric acid. The waste management is then facilitated and fusion is a clean method to prepare your sample. The heat needed to have the peroxide react with the sample is controlled by the instrument in a very fashionable and repeatable way, making it stable and safe. Also, peroxide fusion is performed in zirconium or nickel crucible, which are rather cheap compared to platinum. Now, when you use borate fusion as a sample preparation method for ICP analysis, you simply mix the borate flux, 2 to 3 grams usually, The sample and any additive such as an oxidizer or an unwetting agent, all within the platinum gold crucible. Place the crucible on the fusion instrument. Instead of pouring the fused melt into a platinum disc as seen in the sample preparation for XRF, the fused melt is automatically poured into a diluted acid, and the magnetic stirring agitation is automatically started. Once the sample is completely diluted, transfer into a volumetric flask and adjust the final volume and acid concentration needed.
One of the great advantages of using borate fusion and peroxide fusion is that you don't have to use strong acids such as perchloric, nitric, or fluoric acid. There is no need to heat strong acids for a long period of time in your lab. With borate fusion, you can dissolve any samples within a few minutes using diluted acids. The borate fusion method is very simple. You only need a borate flux, sample, and if needed, an oxidizer.
There's also other benefits of using borate fusion. Since it's automatic, there's no need for supervision during the process. Technicians can then perform other tasks. Remember that this method allows you to dissolve your sample within 10 to 12 minutes. We can then say it's a method with a very quick turnaround leading to low labor costs. In addition, the fact that all labware needed for preparation by borate fusion can be reused or recycled, it gives you a fast return on your investment. Temperature, speed, amplitude of agitation, and the duration of the fusion being automated makes it very user-friendly and safe. Heat being distributed evenly from one sample to the other, the methods are predictable and gives you repeatable results. Once again, only diluted perchloric or nitric acid is used. There is no use of hydrofluoric acid, no aqua regia, and no perchloric acid to deal with, therefore no large waste quantities of acid. Borate fusion dissolves even the most refractory samples such as chromites, zeolite, silica, zircon, and titanium oxide within those 12 minutes, which makes it versatile and rapid. Finally, as a means of summarizing all of this, we have selected a few features and decided to compare borate and peroxide fusion with acid digestion methods. Taking into account that industries are usually motivated by profitability and quality, here is how we characterize both fusion techniques: fast throughput, low labor cost, low waste production, high analytical capabilities, ease of use, complete dissolution. That even though the initial cost may be higher in the beginning, the real cost in the long run is often lower than all acid digestion techniques.
Now that you know how can sample preparation by fusion be beneficial to your laboratory, let's discuss about the 8 factors to consider if you want to perform successful sample preparation by fusion. These factors are sample oxidation, the borate flux choice, flux-sample ratio, the particle size, the fusion temperature, the quality of the platinum ware surface, the cooling rate, and other special keys for ICP analysis. As mentioned at the beginning of this presentation, only oxides are solved in the molten borate flux. However, semi-oxidized samples or non-oxidized samples can also be prepared by fusion. They only require proper oxidation steps prior to fusion. The fastest and easiest way to perform this oxidation is to do it directly on the fusion instrument. The most commonly used oxidizers for the solid dry oxidation on a fluxer are lithium, sodium, and ammonium nitrate. Carbonates and other oxidizers can also be used. The key to perform the solid dry oxidation on a fusion instrument is to control the fusion temperature and agitation at the beginning of the fusion program. As a matter of fact, we have to first melt the oxidizer, which will oxidize the sample. This step is performed at a lower temperature than the requested temperature used for the fusion process. If the fusion temperature is too high, the oxidizer could volatilize or decompose before the end of the oxidation reaction. By the way, the oxidation is a very important step because in addition to not being dissolved in the borate flux, a not fully oxidized samples could react with the platinum ware and cause its deterioration. You really want the samples to be fully oxidized for the fusion process.
Like any analytical chemistry method, you need to select the best dissolvent for your analytes in order to have the highest possible concentration of sample in your solution. The lithium borate flux acidity index may help you select the best flux for your borate fusion method. You can see on this graph a few common elements being analyzed. Each element has its own dissolution ratio based on the flux type. An element with a low oxygen content, such as calcium oxide, magnesium oxide, where there's one oxygen per element, will get a higher and better dissolution in a flux mainly composed of lithium tetraborate. On the other hand, an element with a higher ratio of oxygen, such as silicon dioxide, aluminum oxide, where there's more oxygen than the element, will get a better dissolution in a flux mainly composed of lithium metaborate. However, if you are looking for a universal solution for many different samples, then a 50-50 mixture of lithium tetraborate, lithium metaborate is probably the best option. However, you may have to decrease the amount of sample diluted per amount of flux. It means that if you go for something universal, you will probably have to reduce the sample flux ratio. This example illustrates the importance of choosing the right flux. In this slide, you can see a borate fusion made with iron oxide. In each of the three discs, we use the same amount of sample and same method. The only thing that changed is the type of flux. In the first disc on the top, we made a fusion using only lithium tetraborate. You can see we have obtained a disc with bubbles and vectors showing different oxidation state of the sample. In the middle, we have used a mixture of 50% lithium tetraborate and 50% lithium metaborate. We have obtained a clean disc without any imperfection. Finally, on the bottom, the iron sample was fused with pure lithium metaborate. You can clearly see the disc is impossible to analyze since it has crystallized. Keep in mind that the proper flux will give you the best result as for this dissolution. In this second example, we repeat the same experiment but using a sample made of pure calcium oxide. Once again, the only thing that has changed is the type of flux. In the first disc on the left, we use lithium tetraborate to fuse the sample. You can see that we have obtained a perfect disc that is ready to be analyzed. In the middle, we have used a mixture of 50-50, so 50% tetraborate, 50% lithium metaborate. We obtain a disc that is cracked and that has shown some undissolved particle leading to partial crystallization. This disc can't be used for analytical purposes. Finally, on the right, the calcium sample was fused with pure lithium metaborate. You can clearly see that the disc has crystallized. It is impossible to analyze it. So you can see that the right flux to dissolve an iron or a calcium sample isn't the same. In an ideal world, each sample type would have its own flux to obtain the best possible result regarding the dissolution of the sample. This principle also applies to borate fusion for solution. If your sample isn't well dissolved in your flux before you pour it into the diluted acid, then you won't get a complete dissolution.
The flux to sample ratio is also an important factor to take into consideration when developing a fusion method. As shown in the previous table, all oxides have a limited solubility in borate flux. We can see here an example with alumina. When we change the sample to flux ratio and we keep all the other factors identical, we can see that we don't obtain an homogeneous glass disc when going from 1 gram of samples to 2 grams of sample, which is over the alumina oxide solubility limits in the 50-50 like lithium tetraborate, lithium metaborate flux. As expected, the quantity of undissolved particles is even larger when using 3 grams of samples in the same quantity of borate flux. As we can see in this example, the particle size of the sample also has an impact on its solubility into the flux. By keeping all the other factors identical, like the flux type, flux to sample ratio, the fusion temperature, and all the others, We can see here that for the same sample, just by decreasing the particle size, we have been able to obtain an homogeneous glass disk without undissolved particles.
It is very important to understand that melting and dissolving are two different phenomena. In fusion, you must melt the flux in order to dissolve the sample into it. So the temperature of the fusion process has to be high enough to melt the flux but not the sample. Usually, a temperature around 1000 degrees Celsius is enough. Repeatability is also a key to success for any analytical method. More important than the temperature used for your fusion, your apparatus shall give you precise and repeatable temperature control fusion after fusion. You also have to keep in mind the analytes when you are selecting your fusion temperature. High temperature may make you lose more volatile elements and it will quickly deteriorate your platinum ware.
Talking about platinum ware, it is also important to remember that the quality of the platinum ware surface also has an impact on the final dissolution and then analytical results. If the internal surface of the platinum crucible is tarnished or damaged, the molten mixture will stick on its sides. The consequences will be less melt homogeneity and an incomplete transfer of the molten mixture from the crucible to the mold or the Teflon beaker. In case of sample preparation for XRF, it is important to remember that the mold surface is the perfect mirror image of the final glass disc surface. Any scratches, dents, hole, convexity, or bumps on the mold surface will appear on the glass disc surface. It will influence the distance traveled by the X-ray and affect the elemental intensities. Also, tarnished or scratched mold will then increase the tendency of the glass disc to stick to the mold surface. This could lead to cracked discs. Talking about sticking, it is also possible that you may need to use a non-weighting agent in your fusion mixture depending on the application. The non-weighting agents, which are usually halide, decrease the tendency to stick to platinum ware. The most common non-weighting agents are lithium bromide and lithium iodide.
In order to obtain a stable glass disc, your cooling step must be well controlled. Remember that when preparing a sample by borate fusion for XRF application, the temperature of the lithium borate melt with your sample dissolved into it is around 1000 to 1100 Celsius degree. You cast it then into a preheated platinum gold mold and you cool it down. If you cool it too rapidly, you will induce stress in the glass, thus making it cracks into the mold. On the other end, if you cool it too slowly, you will allow the molecules to reorganize in their lowest energy state, which is crystal, so you will get a crystallized disc. The appropriate cooling step of a glass disc is somewhere in between too fast and too slow. Ideally, you should start to cool the sample slowly, then increase the cooling rate gradually. When running a sample prepared by fusion on an ICP, a few tricks may help you ease your analytical process. On an ICP OES, it is best to keep the TDS under 1% and below 0.2% for ICP-MS, so appropriate dilution may be necessary. In order to avoid deposit on the ICP torch, reduce the sample residence time in the plasma and use high-energy plasma. Also, decreasing the sample flow rate will help to decrease the amount of salt in the ICP chamber. By experiment in our lab, we found that the two best components to use are a cyclonic spray chamber and a Maynard nebulizer.
To conclude, we want to bring your attention to the fact that sample preparation by fusion is a fast and reliable method for both ICP and XRF. The equipment used for fusion is simple, and the automation of the process leads to repeatable results. It also allows you to prepare a wide range of samples with a single method and ease up the preparation of your calibration curves since metric or mineralogic effect are not taken into account. You can expect a quick return on investment since fusion makes the analytical process in your lab easier and because it facilitates the sample preparation and calibration. Okay, this finished the presentation. We are now have only a few minutes left to answer your questions. You can still use the chat box located at the left of your screen to submit your questions.
Okay, Chantal, let's start with the first question, which is, I recently obtained a cracked disc with chromium oxide samples. How can I solve this?
Okay, good question. So if all the other factors are the same, which means same flux, same fluxer, same particle size, cooling rate, and you're just having this problem, the first thing to check is the quality of the mold surface, especially because chromium has a high tendency to stick to the platinum ware, so it will be more easily be affected by scratch mold. So depending on how the mold is damaged, it can be repolished or replaced. Also, you could look at the glass disc fragment and try to see if there is any undissolved particles in this. The undissolved particles also leads to cracked discs. And if the crucibles you used are tarnished, as explained in the presentation, it means that the molten mixture might stick to it, and this will affect the melt homogeneity and the dissolution that could explain the cracked disc. So the platinum ware would be the first thing to check.
Thank you, Chantal.
Okay, we have just enough time for a last question, which will be for you, Philippe. And the question is, when preparing borate solution, do you directly pour the hot borate melt into the diluted acid solution?
Yes, in fact, yes, we do. The important thing to know is that when you do borate fusion for ICP solution, we only use 2 to 3 grams of borate flux maximum. This way, the heat transfer and the heat shock when you pour your melt into the solution isn't big. And also, it's important that your diluted acid solution is stirring, so there's an agitation when you pour. So this will reduce the heat transfer and also help to accelerate the dissolution after.
We are now running out of time, so before we leave, we want to thank you for your attention, and we hope that you enjoyed this class webinar. There are many questions that are still remain unanswered, but as we mentioned earlier, we will make sure to answer them in the upcoming days.
We will keep you informed about our next webinars through our newsletter and our website, so make sure you are registered into our mailing list. Until then, we wish you a very good day.
Have a good day and goodbye.